EEE 120 Lab4 video. So the first circuit we have is adder underscore gen, which is a memory address generator circuit. So it just basically allows our processor to access memory locations both in and out of sequential order. And it has an incrementer function, so we can test it out right here. Click use PC, which is program counter, hit the clock, our adder bus output will increment, resets it. It also has a function where it um, can change the memory reference address so we can store data or arbitrary memory to any location we want to. We can do that by loading the memory address register, putting a value to the data bus, and then clocking. We can see our address bus output C. We can hit reset to reset. The next two circuits that we created in this lab, I won't go too depth. This is our 2-bit bus mux, which is basically our 4-bit mux from Lab 3, shed down to store only 2 bits. And there's only 2 muxes instead of 4. This is the same with our 2-bit register, which I can open right here. Same thing, it's our 4-bit register using only one 2-bit bus mux and then 2 D flip-flops instead of 4. Basically, our 4-bit register shut down to only store 2 bits. Circuit is the controller circuit, and this design will automatically load instructions in hexadecimal numbers, and this is called operation codes or opcodes, and then which is stored in program RAM, and the ROM, which acts as the decoder and the programmable logic for our microprocessor. Basically, this makes our brainless microprocessors from Lab 3 actually be able to read and compute and do the things that we want it to do. You can see I can mess around with it right now. We can change values, load, hit clock. Circuit in the main circuit is our microprocessor circuit and is a more intelligent version of the brainless circuit from Lab 3 as it can actually perform tasks or functions based on the instructions we give it. So in this lab, the given functions were the load accumulator function and the AND function. So here are the waveforms for that, as you can see right here. But also we added more functions to this. We added an AND, a 0, a sub, and a store accumulator instructions. And for extra credit, I did the invert instructions. So here you can see the opcodes for each of the different functions. And in this lab, we had to decode this using the 14 bits that we were given in the lab manual. And for each instruction, we had to create the specific opcode so that our RAM will know exactly what to do and then pass it on to our circuit. To demonstrate the functionality of our circuit, I'm going to fully in-depth demonstrate 2 of the functions of our circuit. So the first circuit, the first function would be our invert function. So it uses the opcode is 0078 for invert. And here's our opcode. Or here's our RAM vals text program. First 0 means load accumulator. 1 is the value that we're going to load, aka the value to invert. 7 is our instruction. So the microprocessor knows what to do with that value, and then 2 is to stop. So I'll simulate that in the digital. So we can run, hit a clock cycle, one more clock cycle. So as 1 is loaded the value, one more clock cycle, 2 more clock cycles, and then it inverts to E. And since the invert of 1, basically you just take all the zeros, make them ones, ones make them zeros, and that seems to check out. I will demonstrate the sub function. Basically, this just loads a value to the accumulator and then loads another value to subtract, and it subtracts from that value. So I could show my opcode and my RAM vals.hex for this. So 0 signifies a load to the accumulator. A in hex or 10 is a value to load into the accumulator. 5 is the instruction to subtract. 3 is a value to subtract from A, and 2 is to stop. So we can hit a few clock cycles right here. So we can simulate 1 clock, 2. So that's A. Our value is loaded into the accumulator. One more clock cycle, another one, and then that's obviously 10 minus 3 is 7, so that's our results. We continue to hit more clock cycles, and no, the value will not change. Briefly go over the other instructions. I'll show you the waveforms and the hex values, the RAM hex values. This is our AND function. We load accumulator, we load 8, 3 to signify AND. We're ANDing 8 with 9, and then 2 to stop. And that I think the result for that would be 8. Zero function, we load 0, or load accumulator. E, we load E, 4 is to 0, 2 to stop. And then that just takes the value and then zeros it out. So the output is going to be 0. So we already went over sub, store, 0 to load accumulator. We load F, 6 is the store accumulator instruction. B is the location to store, and then stop. Here's our AND waveforms with our specific test case in the RAM vals.txt. So obviously the GTK wave uses the RAM vals.txt. Here's sorry, I'll zoom in, just make it easier. So here's our waveforms for AND, 0 waveforms, sub waveforms, store waveforms. Again, here's the entire ROM vals.hex document. Again, here's our invert instructions, and here's our invert waveforms. And this is a picture of the ROM contents. So this is what we loaded into the controller microprocessor. And yep, thank you for watching. This was my EEE 120 Lab 4 video, and I'm Rohan Dominguez. Thank you.